Have you ever stopped to wonder just how vast our universe really is? Its size isn't just incredible, it's almost incomprehensible. We gaze into the night sky, spotting tiny specks of light, not realizing that many of them are entire galaxies. But while the size of the cosmos leaves us in awe, it also presents a rather frustrating truth. The bigger it is, the harder it is for us to explore. Imagine this. Say we discover a planet just like Earth, orbiting a distant star in another galaxy, one that could potentially support human life. Sounds exciting, right? But then reality strikes. With today's technology, even our fastest spacecraft wouldn't reach that planet for thousands, if not millions, of years. In fact, leaving our own galaxy is, for all practical purposes, impossible for individuals like you and me. Let's take the Andromeda Galaxy as an example. It's the closest major galaxy to our Milky Way, located a staggering 2.5 million light-years away from Earth. If we decided to visit it using our current fastest spacecraft, cruising at 28,000 kilometers per hour, the trip would take around 94.5 billion years. That's longer than the age of the universe itself. Even if we could somehow travel at the speed of light, it would still take 2.5 million years to get there. A truly disheartening realization. So, what's the point of discovering planets we can never reach? Well, unless we find a shortcut. Imagine being able to leap across galaxies in a matter of weeks or even days. This is where the fascinating concept of wormholes enters the scene. A theoretical bridge between distant points in space-time, wormholes could revolutionize our understanding of travel, both in space and time. If you've ever watched the 2014 film Interstellar, you've already encountered this idea in action. When a main character Cooper and his team leave Earth in search of habitable worlds, they don't fly through normal space. Instead, they pass through a wormhole near Saturn and emerge in a completely different galaxy within minutes. While this sounds like pure science fiction, wormholes aren't just cinematic fantasy. The concept is rooted in real physics, specifically in Einstein's general theory of relativity. To truly grasp the idea of wormholes, we have to rewind over a century to 1915. That's when Albert Einstein published his revolutionary theory, expressing it through a set of 10 field equations, collectively called Einstein's field equations. These equations describe how matter and energy affect the fabric of space and time. But don't worry, we're not diving into the complex math, just the implications. Picture space-time as a stretchy mesh or fabric. When you place a heavy object, like a planet or a star, on this fabric, it bends under the weight, just like a trampoline would sag under a bowling ball. The more massive the object, the deeper the curve. This curvature is what we experience as gravity. Einstein himself found only a partial solution to his field equations. But in 1916, a German physicist named Karl Schwarzschild managed to solve the equations fully for a single spherical mass. His solution led to the theoretical prediction of black holes, regions where the curvature of space-time becomes so extreme it creates a bottomless pit, disconnecting itself from the rest of the universe. Though this concept was purely theoretical at first, 100 years later in 2019, scientists managed to photograph a real black hole for the first time, proving Einstein and Schwarzschild were on the right track all along. But here's the fascinating part. Black holes aren't the only solution to Einstein's equations. Just as a quadratic equation can have more than one solution, so too can Einstein's field equations. One of these alternate solutions is the wormhole, or, as it's formally known, the Einstein-Rosen bridge, named after Einstein and his colleague Nathan Rosen, who proposed the idea in 1935. So what is a wormhole, really? Think of it as a tunnel connecting two distant points in space-time. To visualize it simply, picture a flat piece of paper. If points A and B are on opposite ends of the paper, the shortest path between them, on a 2D surface, is a straight line. But what if you fold the paper so that A and B touch? You could poke a hole through, allowing you to move from A to B in an instant. That's the basic idea behind wormholes. In 3 dimensions, the distance between galaxies might seem impossibly vast. But if our 3D universe could be bent into a fourth spatial dimension, just like we bend the paper into 3D, we might find shortcuts we never imagined. Of course, understanding higher dimensions is tough. We're all used to living in 3. But let's draw another analogy. Consider a flight from Delhi to New York. On a flat world map, a straight line might look like it should pass over Africa. But in reality, the shortest path, known as a Great Circle Route, passes over the Arctic through places like Finland and Iceland. That's because the Earth is a sphere, and we must account for 3D space. In the same way, a wormhole might offer a shorter, faster way to travel through the 4D curvature of space-time. And this isn't just a theory from films. In 1957, physicist John Wheeler elaborated on Einstein and Rosen's work by giving us the term wormhole. He used the example of a worm tunneling through an apple, cutting across the fruit instead of crawling over the surface. A shortcut, a direct path. We often see diagrams of wormholes as funnels or tubes connecting two flat planes. These help us understand the idea in 2D, but in reality, a wormhole would appear more like a sphere, a distorted bubble where space bends so much it connects two far-apart regions. The movie Interstellar portrays this with surprising accuracy. The wormhole appears as a shimmering sphere floating in space, bending the light around it. And that's no accident. The filmmakers worked with real physicists to make it as scientifically realistic as possible. Great. Let's continue with the next part of the script. Now, while wormholes sound like the perfect solution to our space travel problems, there's a catch, a big one. So far, everything we've discussed about wormholes is purely theoretical. They exist on paper as solutions to Einstein's equations, but we haven't actually found one in space. Not yet. Still, the theory has scientists intrigued. If wormholes do exist, could we travel through them? Could humans one day hop from one galaxy to another in minutes instead of millions of years? To answer that, we have to look at the nature of wormholes more closely, especially how one might be formed. And this is where another fascinating cosmic object enters the picture, the black hole. Black holes are created when massive stars collapse under their own gravity. The result is an object so dense that not even light can escape from it. They create intense curvatures in space-time, exactly the kind of warping that wormholes require. So some physicists theorize that a wormhole could actually begin at the mouth of a black hole. But there's a problem. Everything that falls into a black hole is crushed by its unimaginable gravity. So if you entered a wormhole that starts with a black hole, would you survive the trip? Or would you be torn apart before you even made it to the other side? More importantly, what exactly is on the other side of that wormhole? If it's just another black hole, then congratulations, you've gone from one deadly trap into another. You're not traveling through the universe. You're just falling into an inescapable void. To make wormhole travel possible, we need an exit, something opposite to a black hole, something equally powerful but with the opposite behavior, repelling instead of attracting. And that brings us to one of the most bizarre ideas in theoretical physics, white holes. A white hole is, quite literally, the reverse of a black hole. Where black holes suck everything in, even light, white holes do the opposite. Nothing can enter them. They can only expel energy and matter. If a black hole is a cosmic vacuum cleaner, a white hole is more like a galactic blow dryer, blasting out material and not allowing anything in. The concept of white holes isn't new. In fact, it came from the same field equations that predicted black holes and wormholes. The term white hole was first coined in 1964 by Russian physicist Igor Novikov. He described them as time-reversed black holes, theoretical constructs where space-time is inverted. A black hole's event horizon, the point of no return, traps everything that crosses it. A white hole has its own event horizon, but it's a point of no entry. Nothing can pass into it, but things can emerge from it. So, could white holes be the exit point of a wormhole? The place where you emerge after traveling through a tunnel of warped space-time? That's what some scientists believe. And here's where things get even more mind-bending. Some theories suggest that white holes could be connected to the Big Bang itself. Think about it. What could spew out massive amounts of energy and matter into the universe from a single point? Sound familiar? Some physicists speculate that the Big Bang, the event that created the entire universe, might have been the explosion of a gigantic white hole. It's a bold idea, and one that challenges our very understanding of time, causality, and reality. Another theory connects white holes with black hole death. The legendary physicist Stephen Hawking proposed that black holes aren't eternal. Over billions of years, they slowly lose energy through a process now known as Hawking radiation. Eventually, they evaporate and die. But when a black hole dies, what happens to all the matter and information it has swallowed? According to quantum theory, information can't be destroyed. This is known as the no-hiding theorem, a fundamental rule that says information in a closed system must always be preserved. It can be transformed or scrambled, but it cannot vanish. So, if a black hole dies and releases everything it once consumed, where does that information go? Some scientists propose that it emerges from a white hole, that the white hole is essentially the final stage of a black hole. Matter goes in through the black hole, gets compressed, and when the black hole collapses, it erupts out of a white hole somewhere else in space, or even in another universe. Sounds like science fiction? Maybe. But let's not forget, black holes were once considered fantasy too. For decades, they existed only on paper. And then we saw one. In fact, there's even a real-life event that some scientists believe may have been a white hole sighting. On June 14, 2006, a space satellite called the Neil Gehrels Swift Observatory picked up something unusual. A sudden explosion of white light, a massive burst of gamma rays that appeared from nowhere and vanished just as quickly. This mysterious event, named GRB 060614, had no accompanying evidence of a dying star or collapsing supernova, normally the cause of such bursts. This led some astrophysicists to propose a bold idea. Could this have been the first ever observed white hole? We haven't seen anything like it since. And because the event didn't repeat, scientists can't study it further. But just like early black hole theories, it has added fuel to the fire, keeping the conversation about white holes alive. Now back to wormholes. Even if they exist, and if we can find both a black hole and a white hole to form a tunnel, there's still another enormous challenge: stability. Wormholes, according to current models, are incredibly unstable. Any tiny disturbance, like the presence of a human spaceship, could cause them to collapse instantly. To keep a wormhole open long enough to travel through, scientists believe we would need something very unusual: exotic matter. This hypothetical material would have negative energy density, something that doesn't exist in the known universe yet, but that's required to counteract gravity and hold the tunnel open. Interestingly, in 2015, physicists took a small step toward the real-world application of this concept. Not in space, but in a lab. A group of scientists successfully created a magnetic wormhole in a laboratory. Using special materials like yttrium barium copper oxide and keeping them in a liquid nitrogen bath, they managed to manipulate magnetic fields in such a way that one magnetic pole seemed to be disconnected from the other. Normally, the north and south poles of a magnet always come as a pair. But in this experiment, they appeared to be separated and connected invisibly through a tunnel or wormhole in the magnetic field. This magnetic wormhole wasn't a space tunnel between galaxies, but it was proof that wormhole-like behavior could be engineered in the right conditions. So while we haven't discovered cosmic wormholes, we've already taken baby steps toward building them, at least in fields like magnetism. Even though we've made conceptual breakthroughs, the truth remains: wormholes are still just theories. Despite their mathematical beauty and endless cinematic appeal, we haven't yet seen one, touched one, or traveled through one. And even if we do find them one day, the idea that humans could actually travel through them is still met with deep skepticism by the scientific community. The biggest concern? Survivability. Let's say, hypothetically, a stable wormhole opens up near Earth. Could we just launch a spacecraft into it and end up in a distant galaxy? It's unlikely to be that simple. The intense gravitational forces near the wormhole's mouth would pose immediate threats. The radiation, tidal forces, and space-time distortions could destroy a ship or the humans inside, before the journey even begins. And then there's the engineering dilemma. Wormholes, if they exist, may only last for a fraction of a second. Long enough for particles of light, perhaps, but not for a spaceship. That's why physicists propose the use of exotic matter, as mentioned earlier. Unlike normal matter, exotic matter could provide the negative energy necessary to prop open a wormhole. But there's a big problem. We don't know if exotic matter even exists. It's a bit like planning a trip across the ocean by building a boat out of a material that's never been discovered. And yet, the theory remains. If we ever manage to create or detect exotic matter, wormholes might transition from science fiction into engineering projects. Now, even if wormholes turn out to be a dead end, that doesn't mean faster-than-light travel is completely off the table. Scientists have been exploring alternative ideas, one of the most exciting being the Alcubierre Drive. Proposed in 1994 by Mexican physicist Miguel Alcubierre, this concept doesn't involve tunneling through space-time. Instead, it involves bending it. The Alcubierre Drive suggests a futuristic spacecraft that wouldn't move through space in the traditional sense. Instead, space in front of the ship would be contracted, and space behind it would be expanded. The result? The spacecraft would effectively surf a wave of distorted space-time, allowing it to travel faster than light without technically violating the laws of relativity. Why does this work? Because Einstein's theory prohibits anything from moving faster than light within space, but it doesn't restrict space itself from expanding or contracting at any speed. This is how the universe can expand faster than light, and the Alcubierre Drive would be exploiting that loophole. However, once again, the key ingredient for making this drive possible is, you guessed it, exotic matter. The same material theorized to hold wormholes open. And we face the same problem. It's hypothetical. Plus, even if exotic matter were found, it would take an astronomical amount of it to create a working Alcubierre Drive, possibly more energy than exists in the entire universe. Despite this, researchers are still exploring scaled-down models and alternate approaches, hoping that some version of space-time engineering might become feasible in the far future. So, where does all of this leave us? We are standing at the edge of the known universe, peering into the cosmic abyss with nothing but mathematics, imagination, and a few blurry photographs of black holes. But isn't that how all great discoveries begin? Once, black holes were pure fantasy, products of chalkboards and thought experiments. Then, a century later, we photographed one. Could the same be true for wormholes? Or white holes? Or even warp drives? Maybe. If nothing else, these ideas challenge us to dream bigger, to stretch the boundaries of what we believe is possible. They force us to confront the limits of human understanding and dare to reach beyond them. But here's the most important takeaway. Even if we never reach another galaxy, even if wormholes stay theoretical and Alcubierre drives remain on the drawing board, these ideas still matter. Because every time we chase a theory, every time we test a wild idea, we push science forward. And one day, one of those impossible ideas might just change the world.